Welcome to video number 2 of 1.10, which is looking at the different types of discontinuities. So when we looked at our graph in the previous video, we could see where the graph was not connected, right? Where the graph was not continuous, where it was discontinuous. But example 2 says, what if we just give you a function? Can you list the x values for the graph isn't continuous, and can you classify them as being non-removable or removable? And if they're non-removable, what type is going on? So where do we even begin? So we go back to what we talked about before, when we were talking about vertical asymptotes. We said vertical asymptotes occurred whenever I had a rational function, a fraction set up, and if I ever inputted a number that gave me a zero in the denominator, but another non-zero number on top, then that was going to be a vertical asymptote. I also alluded in the notes that we wrote down here in the last video. Oh, this is what I'm just talking about right now. I'm talking about this thing, right? That if you substitute a number, do direct substitution, and you get a number over zero, well, then that's going to be a vertical asymptote. If you get a 0 over 0, that's an indeterminate form, and that's more than likely going to produce a hole in the graph, a point, discontinuity. So the question is, do I know what makes the denominator go to 0 only? Do I know what x values make the top and the bottom equal to 0? So what we could do is we could take this function and let's factor it out. Because I'm not going to sit here and test all x values to see if I get a 0 in the denominator. If I factor out the denominator, I might be able to get to the answer a little bit faster. So if we factor x squared minus 3x minus 10, I believe you get x minus 5 and x plus 2. That's the factorization of that quadratic on the bottom. So what does that tell us? That tells us that if I substitute an x value of 5, 5 minus 5 would be 0. 0 times 5 plus 7 is going to be 0 as well. So x equals 5 is one of those places where there could be a discontinuity. And at negative 2, at x equals negative 2, that's the second place, because negative 2 plus 2 is 0. Negative 2 minus 5 is negative 7, and negative 7 times 0 would be 0. But remember we said if there's a 0 in the denominator and a number that's not 0 in the numerator, then we'll have a infinite behavior situation with a vertical asymptote. So I need to factor the numerator as well to see if there's any common factors. If there are common factors on top and the bottom, well, then those are going to be deleted points. And then whatever's left over is going to be a vertical asymptote. So if I factor this out, x and x, 40 can be factored into 8 and 5. So I think this is plus 8 and minus 5. So once I do that, I notice, hey, this common factor, if I were to substitute a 5, a 5 wherever I see an x, right? I would get 0 in the numerator, 0 in the denominator. That means I have an indeterminate form, and that's where the hole in the graph is. So I'm going to say with confidence that at x equals 5, because it produces an indeterminate form of 0 over 0, because that's a common factor on top and bottom, there's a removable, specifically, I guess if you want to call it a point, discontinuity. There's a hole in the graph. There's a deleted point at x equals 5. What tells me that? The fact that there's common factors, x minus 5 on top, x minus 5 on the bottom. Because if I substitute this number right here, x equals 5, it will give me a 0 on top and a 0 on the bottom. Okay, so then what's left over? Well, this one's left over. So then I'm going to say at x equals negative 2, because if once I reduce the x minus 5 factors and they're gone, then I'm only left with x plus 8 over x plus 2. So then if I substitute a negative 2, I'm going to get 6 on top and a 0 on the bottom. Well, that's infinite behavior because it's a number divided by 0. And so at x equals negative 2, there is a non-removable discontinuity, and I'm going to say it's an infinite discontinuity. Do we agree with that? Do we see why? Um, if as I try to open my calculator, we'll graph it and see if what we're predicting is actually going to happen. And again, the whole idea is whenever there's a common factor on top and bottom, that's going to, if I substitute the x value that makes that factor equal to 0 into the top and bottom, it's going to give me a 0 or 0. That's a hole in the graph, a removable discontinuity. But once I cancel that out, this purplish circle here, once I cancel that out, then I'm left with x plus 8 over x plus 2. Well, then now, whatever makes the denominator equal 0 but not the top is going to be the vertical asymptote, and therefore that's infinite behavior, and there's another type of discontinuity there. All right, so let's clear the top. We'll quickly do x squared plus 3x minus 40. In the denominator, we'll quickly do x squared minus 3x minus 10. Let's see if we can see it in a Zoom 6. Well, I definitely see in the Zoom 6 window, in a standard window, that there is a vertical asymptote at x equals negative 2 right here. Notice the infinite behavior around x equals negative 2. And I can also see that there's a missing point at 1, 2, 3, 4, 5. At x equals 5, there's a missing point. That's a point discontinuity. So what we predicted actually came true.